currently and with David Holler, and we usually use WebEx.
So maybe we should introduce Zoom in the future.
Yes, this is kind of introduction to Zoom. So anyway, I'll go ahead and jump right in. So what you should see on the screen now is just kind of a BWXT overview. Is that what you see right now?
Bob, yes. Would you mind just putting it in a full screen or presentation mode?
It's going to mess up my
okay.
screen thing here. Yeah, is it big enough for you?
I'm okay. Yeah.
Okay, but you can see it all?
Yeah.
Okay. All right. Well, I just wanted to just do a brief just a plug here for BWXT for maybe those of you who are not familiar with BWXT. Of course, we are considered industry, but maybe a little bit different than what you're used to. BWXT is the leading supplier of nuclear components and fuel to the U.S. government, primarily talking about the nuclear Navy. We provide technical management and site services to support government in the operation of, quote unquote, complex facilities and environmental remediation activities. And we also supply precision manufacturing components and services to the industry and can-do fuel, obviously for our friends north of the border. In addition to our main product lines, and that employs, as you see there, we have 5,400 employees worldwide, 4,000 here with clearances. The majority of those are up here in Lynchburg, Virginia. It's about half that number, about 2,400 or so, work in the Lynchburg area. I actually work in a relatively small group called BWXT Advanced Technologies, and we kind of sit in the middle of all our main product lines. Obviously, the main one being the naval reactors interface. This team of ours, we play a role for tech transfer and engineering services, providing government and commercial interests access to BWXT's vast technology resources. I've listed a few projects here that we're involved with currently. New plant development, that's general. We have we've had contracts with NuScale recently, the past TerraPower. Of course, we had our own mPower small modular reactor, about 10 years ago. We have a emerging business division on medical isotopes. We have a operation that we purchased actually Nordium in Canada, and we are working with that team to introduce some novel methods for medical isotopes. We've done, we're currently working with NASA on space propulsion. We've jumped into the game on advanced and additive manufacturing, and of course there's a lot of activity, not just at BWXT, but really around the nuclear industry to take advantage of 3D printing of hardware. And you might have heard recently we got a large advanced reactor demonstration or development program award from DOE. So we have a gas reactor called a Banner that we'll be developing for them over the next few years. We've also have another project, really the project that Dr. Ivanov and Evan Uva and David Holler are working with me on microreactors. So anyway, just wanted to kind of give you that brief introduction. I'm going to jump into the main presentation. Here it's, as you see, entitled Science-Based Nuclear Design and Safety in an Emerging New Age of Database Analytics. So you can also notice there down below where it says the view expressed herein are those of the author, me, and do not necessarily reflect the views of my employer. So there is a bit of subjectivity in this presentation. And so I have to kind of put that out there to, kind of cover us legally, of course. But as noted in my introduction, I'm responsible for development of safety analysis methods at BWX. And what you all at North Carolina State may not realize is your universities, your nuclear engineering department's important historic role in the field. And by that, I'm referring to really back in the 50s to Dr. Clifford Beck, who I don't know if it was actually formally, your first nuclear engineering department head, but certainly right there at the beginnings of the nuclear engineering department there at North Carolina State. But anyway, it was his efforts that led to the first university reactor, not just here, North Carolina, or it's in the United States, really, and in the world. And afterwards, he played an important role as the chief of Reactor Hazards Evaluation Branch for the Atomic Energy Commission. There he blazed a trail that laid a foundation for safety analysis methods that our industry maintains today. So in a word, the challenge that both Dr. Beck and safety analysts like myself share is uncertainty. And through the development of high fidelity instrumentation and control, we've become accustomed to high precision in science and engineering. For those of us in the business of forecasting, the outcome of low probability events, as is done in safety analysis, such precision will always be out of reach. And so this is, really a presentation that's touching on, modeling and simulation. Maybe, for younger people, modeling and simulation, and science-based nuclear design and safety kind of are the same thing, but it's actually taken a long time to really make claims about modeling simulation being science-based. It's taken a path which I'll go through in this presentation. The part of the focal point on the presentation is really on the nuclear power industry, and so we'll go ahead and navigate to the next slide, and kind of establish the premise of the presentation. Oops, there we go. The nuclear R&D community is sustained at its current levels of investment, largely on the fact that nuclear reactors are operating for the public's benefit, whether that's for electric power or medical isotopes or defense, as I've kind of presented there with the BWXT overview. But as with any hardware, instrument, or part, the utility of modeling and simulation is what justifies the investment. Specifically, it is its role in decision-making. The truism goes back to the dawn of our industry, the form of which is defined not only by the state of the art at any given time, but also by kind of societal priorities reflective in labels like industrial age or digital age, or today's the information age. You are likely familiar with the documentary, The Social Dilemma, that was on Netflix, and maybe the best-selling book entitled Weapons of Mass Destruction. These are focused on the use of information and data, often, of course, generated by algorithms, or in our case, maybe science-based modeling and simulation, or data analytics. The premise of such work is that information is secondary to the physical objects or systems. Here, I'm going to be sensitive to nuclear power plants as opposed to the surrogates in the form of modeling and simulation. Information must not be emphasized over the physical thing that it describes. My goal in today's presentation is to add context in identifying priority pathways for contemporary applications of modeling and simulation, drawing on a review of historical trends and the value proposition for the current and next generation nuclear power plants. So thus begins the history lesson portion of the presentation. regarding the subject of forecasting, you should keep in mind that as a species, human species, we've always had a fascination with predicting the future. Well, centuries ago, we might have looked to the stars for insight. Today, we look at twinkly pixels on a computer screen. The truth is, this transition, from stars to pixels is relatively recent. For nuclear system forecasting, I place that transition with George Philbrick, a name you probably never heard of and never really probably will hear again. But in 1938, he invented something called the automatic control analyzer. He'd spent his career and generate, a fair personal wealth building on this original idea. This is the idea of really the invention of the analog computer. Along the way, with from this idea of analog computer, the Atomic Energy Commission, also be using the acronym or initialism AEC. Researchers at Bettis Naval Lab in Pittsburgh, Pennsylvania, picked up on his idea, and ultimately they built the first nuclear power plant computer model by the 1950s. In this analog generation 0 computer model. So I say generation 0, it's really just generations referring to, as you see my little footnote there, analytical capability distinguished by the scale of resolved phenomena. Generation 0 just being the lowest level that you might otherwise expect. I would refer to as a system level, if that has any meaning to you at this point. Anyway, Bettis in the 1950s created an analog computer simulating a nuclear power plant, where energies and flow were described by voltages and currents, and simulations were designed to be real time because they're just circuitry. This, of course, well, maybe for a younger generation, they don't have a full appreciation of that, but real-time simulation has really only been a luxury of maybe the last 20 years, and maybe less than that. But when I started, it was extraordinarily painful to run, complex nuclear power plant simulations, in a day, let alone, a real-time event that might otherwise last minutes. Go on to the next slide here. All right. So in parallel with George Philbrick's analog computer at Bettis, the dawn of data analytics is taking place through the efforts of Claude Shannon. Now, some of you may be familiar with Claude Shannon. He's kind of a lesser known player in 20th century, technology, technology world or legends. Anyway, he's kind of considered the father of information theory. And again, the importance of really content and efficiency in the communication of information. He worked, I guess, as a electrical engineer and established a theory associated with communication, signal processing, noise, but went beyond that to really almost create a calculus of communication and information. He, along with people like Alan Turing and John van Neumann, maybe of course you might know those names, they work to kind of move the needle on modeling and simulation, and what we have come to today to understand as forecasting. The AC was a primary sponsor. As you might imagine, we're talking about the really late 40s and the 50s. It had an original purpose with the weapons program. But in 1953, we have an Atoms for Peace conference in Vienna, Austria, and interest rises in the application of a digital computer for nuclear plant design and safety. And the AEC establishes a tight relationship with IBM. It's still the same IBM company that competes today on computer hardware and, of course, cloud computing, and they're somewhat behind the Amazons and the Googles But nonetheless, they were out there back in the beginning working with the Atomic Energy Commission to make digital computer to support modeling and simulation for design and safety analysis of nuclear power plants. And of course, one of their innovations was the programming language Fortran. Now I know a lot of you are maybe not even learning Fortran in school, but if you're over a certain age, we all learned Fortran, and some of us still use Fortran codes or Fortran based codes like RELAP 5. That's what I use on a regular basis. But of course, some of the new codes, particularly what I'll refer to later as Gen 4, the computational fluid dynamics codes, they're going to be in a more modern language. Nonetheless, going back to the analog computer story, the analog computers are still, still the only practical tool at this time for simulation. Again, kind of going to my point that digital computing was, while emerging, was one, the programs weren't quite there yet, and two, even if they were, the infrastructure and the speeds were just, of course, way too slow to support even Gen 0 kind of simulation. So you still had these analog computers. And really the practical focus was on control system testing. Hadn't quite realized the full value of simulation, modeling and simulation, but they are, and they understand that they need to simulate to test control systems. Let's see, move on to the next. Okay, so moving into the 60s. Science-based modeling emerges as the development of the digital computer stabilizes. So we have a lot of activity going on in the 50s. Again, IBM is working with the AEC. There are just several, I would even say generations of computers being developed and worked on to this time. And by the mid 60s, it's really becoming practical for a kind of an engineering tool. The digital computer is becoming an engineering tool for nuclear engineers. So the first such code is the Flash code, and it is basically released in 1966. Today's RELAP 5 3D code still has a little bit of coding that can be traced all the way back to Flash. Another example of codes at this time that are being developed are some of the predecessors for like MCMP, which of course maybe many of you use. So you can see that you're not so distant from this history. It's certainly in my lifetime, but it's only a generation off from yours. The more significant outcome of this era is that the AEC is codifying nuclear safety analysis requirements into regulatory framework. This is a response to the rapidly expanding marketplace that's going on right now. So companies like Westinghouse or General Electric and Babcock & Wilcox, which is the predecessor to BWXT, they're out there and working with the AEC, but they're also motivated to develop, which is what is now considered, of course, the commercial nuclear power industry. The requirements the AEC were developing drove the need for code development, computer code development, and of course physical testing to validate these codes. Here I note a span of 8 years. Down here on the bottom, 1966 to 1974, illustrating the rapid advancement of science-based modeling during this era. The latter highlight, this 10 CFR 50 Appendix K, is very significant. Appendix K, as it's commonly referred to, is a legal rule book of sorts containing a mix of science and science fiction designed to ensure nuclear power plant assessments of a loss of coolant accident, or LOCA, had large inherent safety margins. This served to freeze science-based modeling in the commercial industry for the next 20 years. This is my segue to the next slide. During this 2-decade hiatus, and the hiatus for the commercial industry with regard to modeling simulation, the R&D community, and that's mostly the national labs in the US and elsewhere, they dove deep into nuclear safety issues. Now, there's a whole backstory to what really motivated the investment by the U.S. government. Maybe some of you know about the emergency core cooling system hearings. I'm not going to really talk about some of the motivations, just that there was a significant amount of investment by the U.S. and other governments into nuclear safety issues, which benefited modeling and simulation immensely. In many ways, I'd consider it maybe not on par to the moonshot work of the 60s, but it was for our industry it was tremendous and really built several of the national labs as that investment allowed the labs to build facilities to do reactor physics testing, thermal hydraulics testing, mechanical testing, anything that was otherwise relevant to nuclear power safety. For modeling and simulation in particular, you of course have the benefit of computer technology being developed, and I put a kind of a identify a kind of a crossroads for modeling and simulation with the kind of an introduction or invention of the Cray-1 supercomputer. Now, again, younger people won't maybe have a full appreciation for the Cray supercomputer, but that was all the rage. If you were a young person in the 80s, you wanted to work on a Cray supercomputer. And when I got out of school and got to the Idaho National Lab, I could work on a Cray supercomputer. That was just the coolest thing ever, because of course it provided the fastest speeds available in the world. That of course allowed that facilitated what I call Gen 3 science-based modeling. Gen 3 science-based modeling, just kind of think of the RELAP 5 code. That is, that kind of epitomizes what Gen 3, as far as the level of complexity and the fidelity associated with simulation of nuclear power plant conditions and accidents, transients. Unfortunately, all that work during this era was really only to the benefit of the R&D community as a method for capturing data from the large amount of physical testing that was ongoing during this period. Test programs of this era emphasized phenomena associated with locusts. However, events like the 3 Mile Island and Chernobyl accidents that sent even more government funding into these efforts. I consider this period as another kind of data analytics age, as one part data from physical testing, but another part from computational advances, drawn out from innovations with like the Cray supercomputer and such. Meanwhile, industry remains stuck with this old safety analysis methods and greater regulatory burden from the 3 Mile Island 2 accident. And during the 80s, of course, it was really a struggle, certainly economically, and there was a lot of activities trying to figure out what the nuclear industry was going to look like during this time. So through industry's interface with the Nuclear Regulatory Commission, they encouraged them to provide some relief from the conservatisms in that Appendix K methodology, primarily via the knowledge gained over this era, meaning the knowledge gained from physical testing and improvements in modeling simulation. So in 1988, the US NRC presented a new regulatory pathway to allow industry to use Generation 3 best estimate computer codes for safety analysis, providing the code scaling and applicability uncertainty, or CSAU methodology, as one such acceptable approach. The 1988 NRC rule change that allowed best estimate safety analysis methods would open up a floodgate of innovation for the nuclear industry. Now, after this 20-year hiatus, well, at this point, it's about 15 years, but it would take a good 5 years for them to be able to figure out how best to use this rule change. But it opened up a floodgate of innovation. There's a lot of activity. This was about the time that I came into the industry. I graduated in '89 and went to the Idaho National Lab, and really didn't realize the situation the industry had been in. But I did recognize the amount of investment that the Nuclear Regulatory Commission and the vendors, primarily Westinghouse and General Electric, were most evident in my work in the early '90s. And this course, was a very exciting time as far as modeling and simulation and applications of safety analysis methods. Real tangible benefits were being realized at this time because right off the bat, you realize that we can relax some of these requirements on nuclear power plants that were basically imposed through analysis. At this, again, kind of at the same time, or I should really just say that continuously, there are computing progress in computing, faster and better and cheaper computers. And this time we're really looking at moving to parallel computers that were becoming so cheap that it would allow even utilities or vendors, who are really on very tight budgets, to bring the machines in and allow them to do their routine engineering computing, which might include safety analysis. And for the benefit, of course, of their customers. In parallel, you also have really the rise of Generation 4 CFD. CFD really, kind of came into some practical use in the '80s, but until the computers got cheaper and more, massively parallel, they really didn't quite take off. And certainly today they're everywhere. And I know, of course, you have several projects, I'm sure, ongoing at North Carolina State they're very much focused on applications of CFD. And in fact, even 25 years ago, where I'm talking, or 20 to 25 years ago, CFD is being used for resolution of very important nuclear industry questions. I've identified here several. I'll highlight some that I'm more familiar with, like the boron dilution precipitation issues. GSI refers to generic safety issues. The impact of debris during large break loca GSI 191 is rather significant issue that it impacted me from an analyst standpoint, as we had to incorporate uncertainties associated with debris into some of our analyses. Vessel thermal fatigue, questions about the impact of cold leg injections, and that large temperature differences between injection and, of course, the vessels that might otherwise be under thermal stress from an event. Anyway, rather monumental applications, I would say, of modeling and simulation using science and really the state of the art. So by the mid 2000s, you have all the vendors with advanced safety analysis methods of some sort. There's a particular focus on the more routine safety analysis, again, looking at loss of coolant accidents in particular. And these methods are called, best estimate plus uncertainty methods. And they have completely replaced those Appendix K methods that, had been imposed back in the 70s. And it took about, a decade or more after the 1988 rule change to pretty much push them out. Probably around 2005, you start to see not only these best estimate evaluation models, as I maybe more commonly refer to them, not only see them for locus, but you also start seeing them for non-locus, for containment and severe accidents. And for similar reasons, there are, of course, there's greater activity in the area of probabilistic risk analysis. So any kind of analysis which really requires examining a domain of event spaces. Because computers are so cheap, you see a lot of methods that allow the user, the safety analyst, to probe this space to reveal what we may learn about how a nuclear power plant operates, rather than just looking at maybe a worst case scenario. So what you have from all this analysis, all this modeling and simulation, is a lot of information. And it's quite insightful, but we had to, of course, dig at that to really appreciate what we have. What we did find out is that our models weren't perfect, and that they were good enough to satisfy a lot of safety issues, but at the same time, they also revealed certain problems that required more validation and more data. So we didn't necessarily need large scale tests, but we did need to go and get more data to support these models. And we start going through a period of shaking down these models and to continue to improve really generation 3 capability. And in fact, what we have really at the end of this era, and of course the end is 2015, a continuum of evaluation model capability. And really what I mean for that is that typically we put analysis to bins like deterministic or probabilistic, but now we have deterministic and statistical and probabilistic methods. And they really have a mix of how we treat different parameters, in these different realms. So consider that a kind of a continuum of methodologies, which can be customized to particular applications as necessary. And an artifact of this continuum is a notable nuclear safety culture shift. What I see at this time, or I saw at this time, was a de-emphasis on the large break loss of coolant accident as an R&D focal point. Many plants became non-local limited, meaning events that like a pressurized loss of pump coolant flow became limiting events with respect to acceptance criteria. And this then motivates fuel vendors, fuel designers, to make better fuel or higher performance fuel. At the same time, it motivated the U.S. Department of Energy to mechanistically tackle practical plant operation issues like CRUD, grid to rod fretting, pellet-clad interaction, and departure of nuclear boiling through its CASTLE program, which of course many of you are going to be familiar, because I know North Carolina State had a huge role in that, that project. So we're pretty much getting very close here today, and I was motivated to write a paper associated with this presentation because I felt like we were at a crossroads. We had invested a lot, and we'd seen impacts from modeling and simulation on the nuclear industry, and obviously we've seen some incredible innovations coming out of the R&D community, and with data analytics kind of moving in the realm of artificial intelligence and machine learning, I wanted to ask the question in a public way: how do we assess the value to the nuclear industry from the progress of modeling and simulation and data analytics? So here's my attempt. So as the saying goes, follow the money. In our business, that involves a look at the power, performance, reliability, and production of nuclear industry. On this slide, I presented data from 3 metrics related to planning economics. These are in clockwise order: cumulative nuclear power plant orders, net full power capacity factor, and power uprates over the last decades. In each graph, there are distinct periods marked by significant change over a few time periods that I've previously highlighted. Nuclear power plant orders expanded from 65 to 75, kind of representing that bandwagon marketplace period. And we start seeing, as maybe I'll say the post Appendix K period, where nuclear industry really couldn't do much with modeling and simulation and analysis. Instead, they start focusing in on capacity factors, making their own operation and maintenance procedures more efficient. And then we see kind of after the 1980 rule change, that is leveled out considerably. Then we move into this period kind of post 1995, where we see incredible amount of progress with power uprates. And in fact, what you see there is for about the last 20 years or so, about 1,000 megawatts thermal added to the nuclear grid, which of course at this time has been about the equivalent of 7 large pressurized water reactors. So basically, what you see is benefits, or gains by the industry, during all these eras. And I try to compile what I thought the drivers for these change. So there really isn't one set thing. I kind of was, looking at, well, okay, what happens when regulations in computing changes rapidly, and what happens when regulations in computing are stable. So I've identified these periods here. Periods of rapid change appear beginning in the 1950s, and then again in the mid-1990s. Modeling and simulation played different roles during these times. Early, as I described before, modeling and simulation is integrated with a regulatory framework. It really establishes modeling and simulation as an important part of nuclear power plant licensing. It maybe more importantly provides common ground for discussing nuclear safety issues, provides a foundation for the production of electricity via nuclear energy. Later, now in the mid-90s, early best estimate methods are used to claim the more unrealistic components of analytical safety margin for those power uprates and improved performance. Industry periods of stability allowed industry to focus on process improvements related to plant reliability. So we have a period during the 1970s, 1995, again, because of the Appendix K and really inability of industry to benefit from gains in modeling and simulation. Utilities are leading the way, emphasizing operation and maintenance upgrades. Now, again, in 2005, we have some, similar stabilities in methods, and really what you have is these, kind of the stabilizing post 1988 rule change of these best estimate methods as they really are being refined and improved and shaken down, and then proliferated into other domains of application. So expanding the opportunity for power uprates and of course performance gains. So a lesson that I draw from these trends is that better estimates, better forecasts can matter, but not always. The differentiating feature depends on the application and how it is used. Integration of modeling and simulation into regulation is the principal reason utilities are interested in modeling and simulation. Vendors, of course, see competitive advantages to using modeling and simulation to develop better products for their customers. Economics of an analysis can be measured by the figures of merit resolved by analysis and the relationship to acceptance criteria. Acceptance criteria that is, usually handed down by our regulator. When these are small, the customer of modeling and simulation is getting good value from analysis. But conversely, when these are large, that's not so true. Identification of those problems where analysis limits plant operation, i.e., where I've highlighted power, performance, reliability, and production. This is important to industry. Of course, a characteristic of better methods is that they must be cost effective. So there's always an optimization problem that must be solved before new solutions are adopted by industry. As my last bullet here states, science is cheap, but with the increasing complexity, the cost of completeness increases exponentially. So where does this suggest the opportunities lie? Well, I've listed a few that come to mind. The physics domains involved are broad. The first two relate to servicing the current installed fleet of light water reactors for up to 80 years. This includes fully realizing the objectives of the aforementioned CASTLE program and maybe similar programs where we get to look at more practical operations and maintenance problems. And then, of course, just addressing the aging issues in general. And there's a lot of work in kind of predicting when component system structures and components might otherwise require maintenance or maybe even fail altogether, implying replacement. The third one here relates to radiological consequence analysis. This is still largely treated deterministically in regulation. Without all the constraints related to current regulatory framework, the last one provides the most opportunity for creativity. Of course, there are a lot of directions you can go under the heading of advanced reactors. DOE is investing significantly in digital twin technology. I know you all, there's some projects there at North Carolina State on this subject. And of course, the exciting thing that I see with projects like that is that the outcome of research in the digital twin area is not an all or nothing kind of opportunity, meaning that value can be realized kind of along the development path, along the R&D path that comes to manufacturing and safety of nuclear power plants. Okay, this leads to my penultimate slide on data analytics of nuclear applications. Here I'm thinking of emerging methods like AI and machine learning, surrogate models, and generative design. You see, of course, the digital twins here on my list. The first item kind of relates to my previous point about the potential benefits along the way to full feature digital twins. That is model-based solutions used in engineering optimization applications, such as being worked into the design process, to provide rapid solutions. Really, because of course, when we do new work, oftentimes, the solution is not at least quickly accessible through kind of traditional pathways and methodologies, rather through tools, AI and machine learning type tools. We can, I'll use the word kind of shotgun. We can go in many directions with these tools today and benefiting from the computing architecture and through examination of the information provided by modeling and simulation, very rapidly identify optimization that can be immediately applied to whatever engineering problem that we happen to be trying to tackle. Other areas where I see upside potential are cybersecurity, smart sensors, and then dynamic PRA, but the latter of which, dynamic PRA, is really reflecting the culmination of progress with Generation 3 modeling and simulation that began 30 years ago with the emergence of best estimate analysis methods. So, so that kind of brings me to my conclusion slide here. Periods of science and database analytics progress have alternated through nuclear history, leading to today's modeling and simulation capability. times they're driven by technology advances in computing. Other times they're driven by regulatory policy changes. Industry has indeed gained significant benefits from modeling and simulation applications. Operation and maintenance flexibilities be able to be provided by broader coverage of plant technical specifications. It's a key outcome used by safety analysts like myself in preparing licensing documentation for nuclear power plants. And of course, back to the Appendix K and best estimate story, we've been able to reclaim margin by utilizing best estimate methods and better estimates on top of that over the last 30 years, which in turn can be used into reclaiming that unrealistic aspects of models that otherwise were accepted previously. New opportunities, should guide modeling and simulation development. I see, of course, certainly upside to both near-term and long-term activities. We have the operation and maintenance. You hear, of course, today plants trying to go to 80 years, and there are going to be new needs for utilities when they try to do that. They'll always be looking to save, be able to save a little money, be a little smarter. And then, of course, long-term, we have advanced reactors. So that basically, ends my presentation. I'll just leave it on this slide since I don't get too many opportunities to promote the book that Kostin mentioned there at the beginning. But at this time, I'll take questions.
All right, thank you very much for the presentation. As you all know, there's two options for presenting questions to our speaker this week. You can either raise your hand and I'll call on you, or if you would prefer, you can post your question on the chat board and I can read it for answering. So at this time, does anyone have any questions? Feel free to post or raise your hand. While we're waiting, there was one. It was more of a statement that came up, less of a question, more of a statement. But maybe you'd want to comment on it. There was a comment made by one of the attendees about CFD for full-scale nuclear reactor analysis is still pretty far away, and was wondering if maybe you want to comment on, the implications there or what effect that has on.
Yeah, well. Yes and no. Certainly, if you had asked me even 10 years ago about CFD and full-scale nuclear reactor analysis, I would definitely agree with that. The work now, of course, I've mentioned Castle, and many of y'all are familiar with, the tools being developed by NEAMS, the moose-based tools. And I'm working on a project right now where I get to interface with those folks at Idaho National Lab on these analysis capability. There is indeed a place for this. Matter of fact, I kind of alluded to some of the applications for CFD in addressing generic safety issues. Now, even back then, you're talking about really the 90s time frame and since, you're talking about one-off or deterministic analysis. And that's probably still the case where the biggest value from CFD relates to these deterministic analyses. So much of what is safety analysis today involves kind of the statistical applications and really looking at a broad domain of responses. Now that's still, of course, very difficult with CFD. But what you do see today is much more of those deterministic analyses with CFD. So there's clearly progress, and it's going to continue as machines continue to get cheaper. Really, the bottleneck is where industry feels like they can afford new machines. And BWXT just got a new computer, new cluster, and it's probably 5 years behind anything that the university has. So industry will lag, and they're really ones that drive the applications of CFD. But every year there are new applications, and incrementally, you know, we might find in 10, 15 years that CFD and I will say Gen 4 methods, evaluation methods that are used in a way very similar to how we're using Gen 3 codes could very well happen. So for, you know, those of you, you know, in graduate school, you could very well see it in your career. So don't be surprised. So I see the next question.
Okay.
Will NRC eventually accept machine learning in the licensing process? And what are the steps to make this closer? And it's a philosophical question. And so I am probably a bit biased by my own personal experience with AI going back 30 plus years ago. So for my master's work, I worked in, you know, artificial intelligence, Lisp computing, Lisp programming language, maybe. I think it's still, people still use it. Anyway, I attended, you know, several AI meetings, you know, both in the nuclear industry and then what was, you know, the American Association for Artificial Intelligence, those conferences. And it became pretty clear to me by the time I got my degree that the NRC would remain very skeptical about these methods, primarily on the basis that they were just extraordinarily difficult to rigorously verify. And you know, you need to have independent methods to demonstrate engineering verification. And that really is a challenge. Now, methods based on machine learning, what have you, where they can contribute is really kind of upfront. And I mentioned, you know, in the design space, where you were searching for the right place to start. And you don't need safety related tools in that particular case. What you really need is a good characterization of whatever problem you happen to have. And that characterization is really in the form of understanding an optimal arrangement of what are the dependencies that, you know, define the engineering component or process you happen to be looking at. You know, the regulator doesn't get into that so much. But you do have to kind of disclose what you're doing in these particular cases. How are you using codes like MCMP, for instance, or RELAP 5, or even more sophisticated codes? But they don't necessarily have to approve it. So, you know, it may evolve, you know, differently. Again, the proliferation of methods and different methods, and that idea of having different methods to, you know, as a form of verification of an original method. Maybe that becomes more possible now. I'm just, you know, haven't seen it yet, and certainly no one is really advancing that to the NRC just.
Thank you. So we got one more question on the chat.
Okay.
When developing advanced reactors, how should we make use of knowledge and data from the light water reactor modeling and simulation? And how should we measure the applicability of this knowledge, the knowledge you get from them?
Well, obviously, there's a lot of similarities between, you know, different power plants. Light water reactor, you're still, you know, heating up a coolant, you're circulating a coolant. The safety concerns are very similar. You know, the transients themselves can be very similar. So there's certainly a lot of knowledge. I will say, for instance, I mean, in a very practical, I can give you a very practical example of where I'm using light water reactor knowledge to leverage an advanced reactor problem. So I'm responsible for our Gen 3 safety analysis capabilities. That's based on BLAP 5. And through our Empower light water reactor program 10 years ago, I established the software quality assurance for BLAP 5 in its application to light water reactors. So there's a lot of nuance to what that means. Software quality assurance really is a two-step process. One, verifying that the code does what it's supposed to do, or what, and by supposed to I mean what's been documented, and then of course validating that indeed it's worth the application or applicable. As I move into the application of BLAP 5 to an advanced reactor, I have to establish a new software quality assurance pathway. And I do leverage that on a high level where I can kind of eliminate, certainly, well, at the high level, you really have governing equations. The governing equations don't change. So I can do the verification and validation, related to certainly system level type phenomena. It's more or less be the same across the codes. You get into the closure aspects. Obviously, things are a little bit different, but oftentimes the closure models that are otherwise utilized by modeling and simulation are extraordinarily similar. Certainly when it comes to even, verification, it greatly accelerates my activities in that regard. When you're dealing with, of course, different coolants and what have you, the parameters that describe the coolant properties, certainly they're different, but, the processes themselves are still very similar. So what you really gain is really an acceleration because you've been through this neighborhood before. And as long as you kind of understand the differences, that the differences are really smaller than the similarities, you indeed will gain something. Now, you have to turn around and explain that to a regulator. It's a little bit harder, of course. But I absolutely do believe that, having that knowledge of light water reactors is really a big step to helping you, go into advanced reactors. And it's not as big of a leap as it might otherwise seem.
Thank you. So we got one last question that since we're coming past 5 o'clock, and we got one last question that came up on the chat. It seems the last major regulatory shift related to reactor analysis was the acceptance of BEPU-based methods. Do you think acceptance of PRA or machine learning methods will produce similar progress or results?
So like I said, it's well, let me reread that question. This seems last measure. Well, obviously it's a little bit pejorative to use the word last major regulatory shift. Certainly that shift had a significant impact on the application of modeling and simulation, and that was because of the obvious financial gains that industry was able to create by modeling and simulation. I do think it's tougher today. And there was such a huge obstacle created by those early evaluation methods that were defined by law. Probably the biggest one today, with at least the current generation of nuclear power plants, relates to siting. And there's a lot of work right now, but the laws is really established. Matter of fact, the laws basically, describe, these huge emergency planning zones, and maintenance of emergency planning zones is very expensive. And they're really established, at least for the current generation, independent of the power that's being produced. Now, as we move towards smaller designs, smaller plants, clearly lower source terms, there is, you know, the only way it's going to be economical is if you can make emergency planning zones much, much smaller, and eliminate that deterministic analysis requirement. And that's coming. There's a lot of work that's been done over the last few years to come up with really mechanistic source term methodologies to take advantage of that. PRA is kind of part of that. You know, PRA also kind of, you know, triggers something for me. I'm a little skeptical about some of the opinions right now on the use of PRA in the design process. And this goes to my opinion, but historically PRA has been used as a design verification tool. And design verification, as you might, you know, expect, it kind of comes in after you've done the design. And nowadays, there's a lot of talk about using PRA methods to inform the design up front. And if you do that, then you've kind of tainted the design verification methodology that, you know, you normally would use on the back end. So I think, and industry has commented on that issue. So we'll see how that turns out. You know, there's always risk assessment associated with design. It's just not necessarily needs to be PRA. Again, it just depends on who you are and how you interpret that word there. Machine learning, I think I'm just not the right person to comment on that. I was skeptical in the past based on my earlier answer about 30 years ago. I am much more open-minded about that. And some of the math behind machine learning methods are much more rigorous than it was, you know, 30 years ago. Now, you know, part of the process is you have to convince the regulator, you know, of how you apply these things. So we'll have to wait and see. Now, I may lose you guys real soon because my VPN just announced that it's about to drop. So I don't know if you want it would close or.
Well, we're getting close to closing time. I noticed that Dr. Ivanov turned on his microphone. You got any closing comments you'd like to make?
Yes, thank you very much, Bob. That was very good. And with your experience, I think all of us benefit, students and faculty and postdoctoral scholars. Thank you very much for this presentation.
All right, well, I appreciate the opportunity. Thank you very much as well.
Thank you.
Bye-bye.
Bye.
See everyone next week. Bye.